connection between how data is stored and how it physically is represented. It's the same, right? It looks exactly the same. So, for example, I can see here when you're making a new object, now you have to take the decision. In my grid, I'm going to replace the one I have, which is what you're doing, right? You're going and you're saying, hey, grid PQ, now whatever information was there, throw it away and replace it with the new information I just made. Which is fine, but it's not very optimal because you already had the information. So you're sort of going and throwing that information away and making new information and overwriting the information that is there, which it's okay, but I would argue that the better way to do it is to use already the information that you had and change it, right? So in the information that you had already in the grid P and Q, you had the cell, right?
Yeah.
So it would have been easier to get the cell that you had there and change its energy and change its alive state and change its whatever was stored there.
Mm-hmm.
Does it make sense?
So you mean that I just need to use the IJ and change the IJ condition instead of add the PQ?
No, like, look, I think it's correct how you do it. So P and Q are new. See, you're looking at the cell and you're saying, okay, I want around my cell a new point where I'm gonna place a new cell, which is correct. It's exactly how I would do it. But instead of making a new object, instead of instantiating all of a new one, in that part, I'll just go and grab what's already there. So I'll say offspring new object will be equal to grid PQ, right?
Yeah. So in the first step, let me see. The cell as the name is new object, and so you mean I don't need to give another offspring new object, but it's the new object itself?
Well, I would have said, so how I would change your code. I wouldn't need neither the vector, neither the quaternion, because I know where the cell is. It exists already.
Yeah.
Right?
Yeah.
So I can delete that and I can say, okay, the offspring new object, right?
Yeah.
You comment that line as well for the that one, and just make a copy of that line so you still have it.
Line 90.
Yeah, exactly. Comment it out, and then make a copy of, and that line can be replaced. Like comment it out exactly, and then replace it, and say offspring new object or new stuff, whatever you call it. It will be equal to your grid PQ, right? Correct. So this way you access what's already there. Now, you don't need to set the parent because it's already set, right?
Yeah, yeah.
And then what you need to go, exactly as you did it, offspring new object, you need to get the cell component and set the energy, right?
Yeah.
But
you mean this line?
Well, the problem is that line is correct, but for the offspring new object, you need to tell what it is. It's a game object, right?
Yeah.
So in front of it, you just need to go and say, hey, no, where you make it.
Sorry.
Exactly in the code where you had it. You just need to tell that it's a game object. So in front of it, you have to say game object offspring new object equals, not there.
Sorry.
Where, there, exactly. Because it's a game object, right?
Yeah, yeah.
Okay, now it's correct. So we've done exactly what you did, but the difference is that we're using the data that's already there.
Yeah.
It exists. You don't need to make a new object. You don't need to set its position, its rotation. It's already there. Correct?
Yeah, I understand. And do I need to change, give the P to I and give the Q to J, because in the next turn, the offspring cell becomes the mother cell?
Yeah, you can do that, but that means in the loop you're jumping, right? So you're sort of going dun 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 dun, and then you're jumping to wherever you have the new, which is fine. Yeah, if that's what you want to do.
And in the cell split process, another question occurs just like this, because I use the grid PQ to store the offspring cell, and the P and Q is defined by as a random range to I and J. But when I run it, the console shows that the index was outside the bounds of the array. I think
Well,
because
it's exactly what I told you. So this gave you an error because you're making a new object and trying to place it.
Yeah.
And it's also a condition of the, and you have to think of the corner and the edge, right?
Just so as the neighbor condition.
Yeah. So what if I am on the corner, right? Yeah. Do you understand what I'm saying? So when you are on the corner,
I is equal to 0 and J is equal to 0.
There you go. So let me grab a big and the screen and explain you the problem. So imagine this: you have a grid of points.
Yeah.
And you want to do the 9 neighbors around. If I am here, that's fine. I can get my 9 neighbors.
Yeah.
But what happens if I'm here? I can get just 3 neighbors, right? So if I am in this condition and I'm asking for a neighbor that might be here, it will give you an error. It's going to say, hey, index out of bounds. There's no one there, right? And there will be the same issue if I'm here. So if I'm here, I have 4, 5 neighbors, right? But I don't have one here and I don't have one here. So it's gonna give you a bunch of errors. So there is a trick to solve this. You can make almost like ghost cells. So you can make an extra empty row. So think of this that is empty. All around my grid, I can place ghosts. So they don't exist, which is a way to do it. But the best way to do it in your code is to check for those conditions. So obviously these 9 makes sense if I am somewhere in the field. But if I am in here, my random range cannot go to -1, right? Yeah. It can only go to +2, right? And it can go, yeah. So you have to think of these corners and the edges. Otherwise, it's always going to give you some error.
Okay. And let me see. So I just need to do the if condition and calculate the corner and the condition.
Correct.
Yeah.
Correct. So you have to do the corner and the edge conditions.
Okay. And now I think the problem mainly exists in the cell split process and
Well, give it a go to fix those and see if it's a bit better, okay?
Okay, I will try it.
Cool.
Thank
well
you.
Done.
Thank you. And I think Jiadong could share his screen to show.
I use different logic, which with you talk to us. Yeah. So I'll share my screen.
那我们的问题真的多。我们应该是。
Yeah. So this is about the game of life development, the rules. So we can see if the initial pattern is 6 mother cells, it just develop once. So there is. So I introduce our rules so we can see the different. I just try to the first rules and second rules to distribute the energy randomly to the initial mother cells and split to the 8th grade around the mother cells randomly. So we can see every time I run the program, it will develop different pattern randomly. Like there are some quick development, just stop. Yeah.
And these are very interesting. The key is also at some point to get out of randomness. So at some point you need to think of what's the logic for not having randomness. You have to develop some type of an algorithm, some way of thinking about it, where you can introduce rules that are specific to what you're trying to do in the project. So your things become informed by some type of computation. And again, start to read computation books, like the ones I showed you with the computational beauty of nature. It gives you a set of algorithms that are super interesting. There are also others where you could try to implement some type of intelligence, right? Some types of decision making. And I think this could be the next step. And I can show you how we can write a genetic algorithm. So we can give the cells a target to do something, right? A behavior that gives them a goal, right? Let's say the goal is to occupy the left corner, or the goal is to make a circle, or something like this, right? So then we can start to give them an intelligence, but start to write the rules of what could the cells do together as an organism. So what would be the organism target? What would they want to do? And you can play different games. It can be a space occupation, so they want to occupy certain zones. It can be neighborhood conditions, so somehow you want the cells to align or to do certain ways of, and you have to sort of go through this and think yourself, like, okay, what am I going to do with this computation? Like, what's my end goal, right? And I think it's going to come from your project somehow. Whatever you're doing with the project, it has to come from there.
Yeah. So now the problem is the first. Wait. Oh, okay. Yeah. So we can see the neighbors and the cell energy. We set the initially total energy is 20. But in the initial mother cell, sometimes the cell just have 0 energy. Because in the Unity script, I don't use the I don't know how to use the sentence to divide the some numbers of energy from the total energy. So I just write the this function like the problem of the function is just maybe sometimes it will choose the 0 because yeah.
Well, again, you have to write the logic for it. So if it chooses 0, you can do an if statement and say what to do if it chooses 0. Or something like this, right? You have to think of these conditions where the logic breaks. And again, it's something that I can't really help with. You have to sort of yourself figure a bit out what the logic is. Or in a different way of saying it, you have to figure out how you want the computation to unfold, to sort of go. And again, it's actually these edge conditions that you have to think about when you're in a corner, when you're in a field, or when you set an energy to 0, or you might set it to negative. And again, it's a bit up to you to think about that. Like I can't help with that, to be honest. But I think again, like keep trying and try to figure out what things work and why they work. And it's like any experiment. You have to try a few things, like try 10 things. And I promise you, if you try them and document them, like I tried this, I tried that, and present it, you're gonna get a lot out of the conversation with me, with Alex, with Mustafa, with Theo. If you do this experimental approach of trying to do little tests, prototypes, and you discover things by doing, if you talk about them, you're gonna find the solution as well.
Yeah, so I think we'll have a try again. Yeah,
that's perfect.
Yes, and just we need more time to learn the Unity script and C#.
That's normal. I think that's
it's really uncomfortable in Unity script. Yeah, I'm not so familiar with the how to write the logic. So yeah,
it's normal. It's normal. I think you're going through what everyone goes through when they're learning something new. So don't be discouraged. It's a good sign. It means you're doing right. You're trying things, so it's okay. Cool.
Okay, thanks. We'll think about it. Yeah.
Does anyone else have questions that they want to share or?
Yeah. Can we start?
Okay. Yeah, please.
Can you see my screen?
Yeah. Different state of water 3.
Sorry. Yeah. So we'll keep on the water simulation. And we use the flocking behavior as our reference. We use its alignment force, but it's very small in our water simulation. And the cohesion force, which called attraction force in our simulation. And also we add another function called border, which means the water, when the water reach the edge of border, it will be bounce. And this is our rules. The one is alignment force. And the alignment force is very small, just make sure the water can move towards one direction at the beginning, or they will be very dispersed. To make sure they are in a container. And the rules 2 is attraction force. And the attraction force, when it's very, it's influenced by the maximum speed and the radius, attraction radius. And when the, it's not the maximum speed. It's influenced by its attraction force and the attraction radius. And when we use a very small force, it can be a low speed expand. When it's big, the speed expand become very fast. And when the attraction radius become more big, it can influence more neighbors between them. So that make more unstable state. And the rule 3, we add a border, but there are many ways to add this border. We just use one way. We use the cross product. That means when it reach the border
boundary. Yeah, you flip it.
Yeah.
Yeah.
But we
Well done.
reflect in a random way. The vector is random.
Well, I'm gonna show you today a way to do it a bit more that is less random. But with cross product, that's a really good way to do it. So you have a vector that points, and cross product sort of gives you the 90 degree. You can also do the dot product, which also can help you. But we're gonna look at how we can do a way of dealing with this border today.
That will be very nice. Will be very helpful for us. Yep. But now we use
different ways. We got a bounce. Actually, the border was affecting very much the behavior of the particles, and they started to moving on the same direction without the cross product.
Yeah, because the trick with this is that you actually don't want to do the cross product, because imagine I'm hitting the border, right? And you're sort of telling it, well, bounce back, right? So what you want to do is to allow it to go beyond the border and have a force that slowly pushes it back. So you have to calculate a vector that is orienting around, and you can do that. I'll show you, or that's my plan for today. I want to show how we can sort of move them back, and the trick is to use the seek function, that you don't hit the border, bounce it. You have to sort of go, okay, you've gone beyond border. I'm gonna give you a seek vector that becomes much larger than your velocity and slowly turns you back. And again, it's a matter of thinking how this works, because when you do the cross product, you will just bounce back.
So use the seek force. It can turn around. It can turn back smoothly.
Yeah, but in the seek force, you have to put a vector. So you have to calculate the vector. So imagine that's the border. My particle comes, and from the border, I need to calculate a vector that is opposite from that, somewhere pointing back, and give that as a point. And I say, okay, now my thing comes, and you have a seek for that direction, and it will slowly, so it'll go beyond the border and then turn. The border is anyway an artificial construct, right? Like I can allow it to go beyond, right? I don't have to worry about, okay, this is your border. I can use it just as a way to turn the particles.
Yeah. So so you use the seek force, which is the same force in the alignment force, the separation force they used before. So
exactly, and the beauty of the seek force is that you're not giving a hard vector. You're not telling go there. You're just giving an orientation, saying, okay, orient yourself towards something and slowly move towards it, instead of going, oh, you've reached here, bounce there.
Yeah, I understand. And we continue. This is our rule 3. And we use this border to see if it's in a larger container. Behavior is different when it's in a smaller container. So, and rule 4, we introduce the temperature into our code. The temperature can influence the max speed. This can influence or the forces, because the forces is calculated by the speed and the acceleration. Yeah. And also when it turn to phase changing, that means the temperature reach these goals, it will influence the particle size.
Yeah, makes sense.
This
Can I say something for
yeah.
just for, and again, I'm being pedantic here. When you do your presentations, especially that everything now it's on Zoom and whatever, we use the whole page. Do the text big. Because I'm looking now, like I'm like, what's there? Like, okay, I have bad eyesight as well, so like, what did she write there? So be like, look at this slide. You have a lot of white space on the left and a lot of white space on the right. Why don't you make it bigger? Use the whole page.
Okay, sorry, I will take
It's
care
okay.
of this.
No, it's okay. I know you're probably doing this really fast, right? Like you just put things together.
Yeah.
But think also, and it's funny. This problem I have it also at work with my team. So my team is usually like your age. They're very similar. So we have to put client presentations, and the clients are usually old, like 50s and 60s. So imagine they have even worse eyesight than I have. And sometimes they're not even on a computer, they're on a tablet or something. So then they really don't see anything. But be very clever. If you have a page, use the whole page.
Okay. And this is show how our temperature is working. We firstly calculate the change of the temperature. We have a slide of the temperature, like here. You see this slide? So this temperature can calculate, when you change it, can calculate its difference, and it will influence the increased value, and that will influence the maximum speed. We do this because we think the temperature is related to the energy. So get the temperature means get the energy. So the energy should transform into speed and the forces, this to, and the kinetic energy. Yeah. And here shows how this temperature influence the speed and the size of particle using some math knowledge. Yeah. And the temperature follow a very basic rules, like when the temperature is very low, the ice in different phase changes. When like in the ice, when the temperature is higher, that the speed would be faster, but they have different influence value in ice stage, in liquid stage, and the gas stage. Because this three stage, the temperature influence they in different times. This is our rules.
Yeah, I understand.
Yeah.
Seems logical.
Yeah, and here we did some simulation. Sorry.
You have to full screen.
Okay.
Press full screen.
Here's the ice stage.
Nice.
We changed the alignment radius here. The alignment radius is bigger. it will be more stable.
Mm-hmm.
And next is liquid stage. Here we change the attraction radius and the attraction force, make it can recognize different range of neighbors. And it is always rotating. We guess it's because the border we set. And you see now our simulation didn't have any collider,
Mm-hmm.
and that's what we have need help in the collide.
Okay. Yeah, we're gonna look a bit on how we can use the collision events.
We tried collision.
That-
Yeah, sorry.
Yeah. No, we tried to add that with different ways, but it didn't work.
So how did you try?
With get component, sphere collider.
You see the problem? You didn't document it. So if you had a few slides with this is the code I tried, this is what worked. You have to do also this part as well.
Yeah, I sent an email to you before.
I know, you did.
Yeah.
But you also have to put it in your presentations.
Oh.
Yeah. Also, again, like I'm helping you, but also I'm telling you, Mustafa, also Alex, they're quite good as well. So they can also talk to you as well with solutions. So you have to sort of, again, like it's the nature of research. You have to document the things you do. And I'm telling you, it's not because I want you to spend time grabbing screens. It's because it's also how you learn. At some point, because of this process, and it's a process that works. Like, I guess you're doing the seminars with Theo, right? So there was one seminar on the scientific method. I don't know if you did it or not, or if you remember about it. About this sort of approach of solving problems in the scientific way, right? Where you do iterative experiments and you look at what each experiment gave you and what steps you took. And by just documenting, looking back, you build the knowledge, and at some point, you get the answer. And it works. It really works. It's how we develop most things today. It's a good process. So, yeah, document some of these. Document how you did it, and I promise at some point you won't need me. You won't need any of us. You're going to be like, this is what I have to do. You have that eureka moment, like,
We have the document of the C-sharp. You want
Yeah.
see later. I have it in the code.
Do you want to share your screen or?
Yeah, or if you want to finish and I can share later, whatever is more convenient.
Yep. But I have to find. Oh, here. Here we try this. I think we delete.
Yeah,
Oh no, here it's here. Yeah, Octavian.
yeah,
we tried this way.
And after initialize, like get component and.
Yep.
No, this is not full. This is not the full method.
But in your function, you're just enabling the collider. And it's impossible to be enabled because you never enter collision because you don't have the collider on. You see the problem? So the game object has a collider that's turned off. So it can never enter into a collision because its collider is off.
But this enabled equals true, isn't it true? Correct?
For sure, but the function on collision enter is never called. I can have a function in there, void blue sky, right? That the condition for that function to be actually called is never called. So a condition for this function on collision enter to actually be triggered is to have a collider that's enabled and also a rigid body. No worries, I'll show you today.
Okay. Yeah.
Okay. But I can tell you that your function on collision enter is never called. If your collider is not turned on, you'll never be called because it just doesn't look for that.
You mean we should call this function into our start function or update function?
That would be a way to do it. You can in the start function enable the collider, or on the prefab you never disable it.
Oh, we can
Yeah.
in container in the grid we update it or make it enable.
Yeah. So you have to have the collider on at some point, which cannot be in the on collision enter because that on collision enter is only called when two objects that have colliders both have their colliders on. If one object has it on and another is off, as far as this function on collision enter is concerned, the collision never happens.
Oh. And how about the rigid body? Should we code rigid body encoding?
No, you don't need to code it out. Don't worry, I'll show you today.
Okay.
But again, some of the things. So, for example, okay, I'll show you today how to do it, but also develop this ability to search yourself for answers. So one of my first thing I would have done, I would have searched for Unity collision event. And there's so many tutorials on how Unity does collision. And if you go through them, at some point you're going to go, aha, this is how it works.
Yeah, with so many tutorials.
Yeah.
Found it. We tried many.
Ask many people.
Yeah, but it's okay. It's also this. You need to develop this ability as well to search for answers. I think you're as clever as anyone else, so you figure the answer as well.
We have.
You don't need my help, or at some point you're going to have the ability to solve the problem yourself. Like, okay, I know how to look into the documentation of Unity. I know how to look to GitHub repositories. And,
we also have some problem in mesh rendering. Tyler, can you share your screen?
Just a little bit, if the time is okay. Yeah, you need to stop the share. Yeah, okay. For the color coding part, because we set temperature with different speed. So I'm thinking to use the speed as a variable to set the different colors, to determine the different colors. But I search online that it's not, because I think the problem is a little bit specific, and I'm trying to use your method of the remap, but it seems not working. And when I search for the tutorial, it's just the lerp color. It's like they change the red.
Yeah, you can use lerping as well. Yeah.
But the problem is like we want to like use color to differentiate different speeds for the particles. So in this way, I'm not so sure how it's gonna work. I actually tried like 2 days, but it's not success.
Okay, so, but again, I'm gonna say the same thing. Show me what you tried.
Okay, for now the code is it's like this part, but it's actually followed your code, but just change the variable to speed. And okay.
Okay, but I understand what you're trying to do.
Okay. And we set the private float for no, but yeah, we have the variables of speed, but yeah, but how it's gonna like control with such as the lerp color, but how to set with different speed to show different colors.
Okay, I understand. I'll prepare something for next week that can apply to everyone. I'll prepare a tutorial on dynamically changing mesh colors. Yeah, it's quite an easy one.
Okay, thank you.
I understand what you're trying to do. Yeah.
Okay, thanks.
Cool. Okay, anyone else has questions or want to share something?
I have one more question. Sorry.
Yeah.
Yeah. We are just now found that this always rotating, but we cannot find the reason. We are just guessing. It's because the border.
Yeah, I can't tell you also why. Again, I'm telling you, you need to do a few experiments to see. Yeah. Cool. Okay. So next team.
Okay. Thank you.
Do you have some questions?
Yeah, we have some questions.
We have some question about the game of life code.